Okay, so we can begin. Are you able to share the screen?
Let me see if I can here. Unfortunately, I was trying to see on another machine what you can see. Are you seeing the slides properly?
Yeah, I can see the first slide.
And nothing else. It's just basically the first slide.
Yes, just basically the first slide.
Okay, good. All right. That seems like that's going to work then.
Okay, so
Pardon?
welcome everybody to the third talk of today. We will be listening to Cliff Burgess from McMaster University and Perimeter Institute, and he's going to tell us about axiodilatons, a dark horse for the dark sector naturally. So maybe I will send you a reminder when 5 minutes are left.
Well, yes, that's it. The target is 45 minutes, right?
Yeah.
Okay, I'll turn a timer on here so that I'll also have a separate clock going, and I'll have some advance warning that it's going to run out. So just give me a second. Sorry. All right, now we're good. All right, good to go.
Okay, let's begin.
Are you ready? Okay. So thank you, first of all, for the invitation to speak. This is one of the great things about one of the silver linings of the cloud of COVID is that there's so many more online seminars that where physical presence, although I think I prefer physical presence, it's not required. And so that it broadens your audience and it broadens the number of speakers you can get. So I appreciate very much allowing me to participate. And so the story I want to tell today is axiodilatons, the dark horse for the dark sector naturally. So it's a model essentially for the entire dark sector, dark energy and dark matter. And I hope to convince you that it has actually a number of very appealing features, particularly in the view of the anomalies that we see in the cosmological data. But the model is not being proposed aimed at the anomalies. There's a completely different motivation for examining these kinds of models. So for me personally, I find it very rewarding and suggestive that the models that are being proposed for other reasons actually seem like they resonate with the things that the observations, the hints that observations give us about how lambda CDM uh, could be failing. So the way so has the slide advanced for you?
No, we are still in the first slide.
All right, so that's something. I have this. I can kind of see that there's probably two windows, and I'm not showing you the right window.
Maybe you can just stop the screen share and then try again or join again.
Okay, that's sorry. I'm doing this in a place where every time that I take my mouse off this, there's two screens, and the directions are not the ones that I would normally have chosen. So, all right, let's try it again. So that's screen two. Try this one.
Yes, the first slide has come.
All right, so there's something wrong with why is this? Ah, I think I know what it is. All right, I'm a bit baffled here. I'm sorry. I'm advancing the slides on PowerPoint, and the screen that is you're viewing, which is the screen that would have been the one that that I would normally use in a talk, is not advancing at all. So let me try. Maybe what I'll do is I'll show you the non-show screen, but the screen that is
I think that should be fine.
if I could find it is the problem. I think what you're gonna get a lot of clutter, I imagine. So it's
Yes, this is a different slide now.
yes, but you're probably seeing a lot of things besides the slide, right?
Yeah, but it's still fine, I guess, because the most dominant portion is the slides.
Right. I'm gonna try one last thing, and if this doesn't work, then I'll give up because I know this is nothing more annoying than someone futzing around. Um, I should be able to, I think, choose a subset of the screen. Here we go. So just bear with me.
No, sure. Yes, the next slide has come.
All right, and now you should just be seeing only that slide. Is that right?
Yeah, only the slides. That is correct.
All right. And before I start, let me also just advance the slide and make sure that that works. Did it go back to the first slide?
Yes.
Excellent. All right, now we're in business. Thank you. Sorry for that. So I'm trying to sell you a model, which I have a very I think it has a lot going for it, and I think the lessons to be drawn from this model are more than just the model, which is what the talk mostly will be about. So the second slide here is another way to think about the things that you learn from this model, and it's about what can we learn at low energies about what we see in cosmology, which is the lowest energies possible, given what we think we know about what's going on at higher energies. And that's kind of the paradox of cosmology from a particle physicist's point of view. We hope to learn a lot about particle physics from cosmology, but normally what happens is that short distance physics doesn't show up in long distance physics. That's why we didn't have to understand nuclear physics to understand atoms. Decoupling is a phenomenon that nature has. And so normally what would happen is that the longest distance physics doesn't care at all about the short distance physics. And the opportunity of cosmology is that the things that cosmology likes in many models are things that are difficult to get at low energies. And that's the informative part. There are some things at low energies that can be sensitive to UV physics. For example, the properties of an atom to care about the charge of the nucleus. So you had to know something about the nucleus. And it happens that those specific things that are UV sensitive are things that cosmology responds to that make the difference in the success of a cosmological model, such as very light scalar masses or small vacuum energies. Those are unusual from the point of view of low energy limits, but they're something that cosmology seems to like. Now, saying it that way makes it sound like very similar to the swampland program, which purports to be describing, giving you information about how high energy physics affects low energy physics. And I am definitely not doing that. So this slide is supposed to highlight that I would call this the Highland program, not the swampland program, because what I'd like to do is use symmetry arguments and very generic properties of things that we know about high energies as my clues, as opposed to in the swampland program, what people do is they assert that there's a class of low energy theories that cannot be completed to the UV. And so they're asserting that the things that are interesting are the things that are very, very UV sensitive, the things like difficulty getting to Sitter space. And if you think about, for example, quantum chromodynamics, a theory we understand very well, there are very robust low energy predictions, such as soft pion theorems, which are consequences of the symmetry breaking pattern of QCD. And then there are very detailed predictions like the mass of the proton, which depends on all the details of QCD. And so the swampland people are more or less saying that these things like the Sitter space are like the mass of the proton. It depends on all the details. And so you need to know the details. And that's why thinking about whether or not you're embedded in a UV completion is useful. Whereas I'd like to take the point of view of the soft pion theorems, that I just want to focus on symmetries. And so anything at high energies that has these symmetries will be the thing, will have the same consequences. But these are symmetries that are coming from what we think are generic to high energy physics. So that's the distinction I'd make between this and the swampland program. All right, now let's see if I can advance the slide again. You now see figures full of faces,
Yeah.
I hope. Good. All right. So these are my collaborators, and what I'm describing is actually not just one thing. It's part of a long cluster of ideas, which is a long development. And so it starts with class of models which I think are exploiting these symmetries and the symmetries themselves that are coming from string theory. I'm going to take string theory as my template for what's going on at high energies, although really it just relies on the symmetries. And so this leads to a class of theories involving light scalars, axiodilitons that I'll talk about, and the properties of those were explored in these papers. And then the cosmology that leads to, because you'll see that it's a fairly surprising construction, that there's particles that are coupling quite strongly to ordinary particles. And so you would think that they should be ruled out, these models. And the surprise is they're not. And so there's lots of places to test them, because there's many ways in which they affect observables. And the cosmology for that has been explored with these lovely people. And the original issues of the symmetries are coming from much earlier work. All right, so my message is, I'd like to ask what you can say at low energies, given that you think you understand things at high energies, and that's really going to be a power counting argument. I want to argue for you that it's possible to identify the kinds of things that could be competing with gravity. If we're in the business of testing gravity, as we are in cosmology and when gravitational waves and in the solar system generally, it's useful to know what are the things at low energies that you're sensitive to. And so there's a bit of a surprise in this answer, in that the most of the models that people are calculating with do not include the interactions that are most competitive with gravity at low energies. And so this line of argument will point you towards a class of theories to think about if you're interested in low energy deviations from general relativity. The ones I'm going to be focusing on are motivated by symmetries and a mechanism, and that mechanism is basically a general mechanism that has been found about 20 years ago, but seems relatively little known, for suppressing the corrections to a scalar potential. And it comes from the interplay between scale invariance and supersymmetry. So if there's time, I will talk about what that motivation is here, and then the models to which it leads. And so there's that one model I'm going to talk about in particular in more detail is going to be will be a specific application motivated by these symmetry arguments. And then I'll describe the cosmology you're led to, and it has this surprising efficiency in the sense that you'll see that the first line of argument points to you should really, the things that want to compete at low energies are theories that have two at least new fields, scalar fields. And then it's kind of irresistible to say, well, if you've got two things, there's two ways we know general relativity actually does fail. It doesn't describe dark energy, it doesn't describe dark matter. Maybe those two things are the two things that we needed at low energies. That turns out to be actually a very efficient, but also reasonably successful proposal. And so that's the model I'm heading towards. And if I run out of time, which there's a good chance I will, given I am slow, what I will cut out is the middle part. But the slides, if you have this access to the slides later on, we'll have the slides for the middle part. But that'll be the thing that'll go, because I'd like to be sure that I show you the consequences of the model. And I'd like to start with the first part, which is motivating the classes of models. And then the third thing would be the middle part that I might miss. All right, so let's dive right in. So if this is the part of the talk where I want to go through the argument about what should we expect to see at low energies, and I'm doing it in the context of we have a theory, we're at low energies, it's got the particles we know about, the standard model, it has general relativity, and possibly some scalars. So I'm going to focus on scalar fields as being the new fields we're looking at, and ask what could they look like at low energies. And the point of this section will be that that's a very counterintuitive thing for particle physicists. Tend to be the ones who sneer at theories with light scalars, because the way we would normally say it is that you have to tune the vacuum energy to be small, and then you have to tune the scalars to be small. So you're doing epsilon squared physics. It seems like it's doubly unlikely. And I want to argue that that's actually the wrong way to think about it, that there's really only the smallness of the vacuum energy is important. And once that's true, it's very easy to have light scalars. So that'll be point 2. But the things that want to compete with gravity are the ones that have the interactions that have two derivatives, so sigma model kind of interactions. But for those to exist, you have to have at least two scalar fields. And then I'll zoom in on a minimal model, which has 2 scalar fields, and it's well motivated for other reasons, these symmetry reasons that I alluded to as the middle part of the talk. So at low energies, if you kind of wrote down in a derivative expansion what the Lagrangian might look like for a bunch of scalars, I'm calling them phi, they're dimensionless, and the metric coupled to each other, And I'm taking the point of view, which I think you have to take, that we're looking at the low energy limit of something more fundamental in the framework I'm thinking about. Then what I've written here is explicitly is a derivative expansion. There's a potential term, and I've organized it in a way which is as natural as possible. So there's an overall scale V, which sets the size of the potential, but I'm imagining that as a function of these dimensionless fields phi, U is some function with, if you expanded it in powers of phi, has only order 1 coefficient. So there's nothing particularly special about the dimensionless coefficients in the potential. So it's a generic thing, and it'll be technically natural. The kind of thing I might be doing is that this might be an axion, and maybe these potentials are trigonometric or something, but I don't want to use detailed forms for the potential because I want to look at what's generic at low energies. Then there's the 2 derivative terms, and these consist of the Einstein-Hilbert action itself, of course, but also the sigma model interactions for the scalars. And then there's 4 derivative terms, which are curvature squared, and there's many I haven't written here. There's things involving 4 derivatives of the scalars, there's 2 derivatives of scalars, and curvature terms, and so on. And that's all hidden in the ellipses. And I've chosen the scale that could have appeared in front of the kinetic energy to be the Planck scale. That's for simplicity. It could have been smaller. But the generic thing that comes down from low energies is this will be as weakly coupled as it can be. And so this is kind of not a radical assumption, but I'll do that for simplicity from now on. Now, the naturalist problems are normally associated with the potential. So the scale V can't be, in a derivative expansion, V can't be also of the Planck size, because when we solve the equations of motion for the curvature, famously we get a curvature which goes like V squared over M Planck. And so in this derivative expansion, the curvature is a derivative, and so it had to be small compared to M Planck. And so if we're going to ask for the derivative expansion to be valid, then it has to be true that V is small compared to the large scales of the problem. That's basically contains within it the cosmologic constant problem, but it's the naturalist problems to do with scalars are all coming from the potential. It's a thing that wants to dominate a derivative expansion if you're doing a derivative expansion. But one of the observations is that once you've made V small, so you've made the curvatures that come from it small, you've also made the masses for these scalars small, because they appear in the equations of motion for the scalars in the usual way. And because the scalars in this case I've chosen to be coupled with Planck strength, so M Planck is in front of the kinetic term, the masses that you get are generically V squared over M Planck, and so that would be the Hubble scale. So the lesson of this kind of a description is that if you've understood why the potential is small, and there has to be an understanding of that because it is small as far as we can see in cosmology, then if you have any gravitationally coupled scalars that are around, they will for free be light, because it's not a second adjustment to make them light. It's really just a consequence. It's one of the side effects of having a low energy potential, where the overall scale is small. All right, that's an old observation, but it's something which particle physicists in particular tend not to approach it this way. And so what I'm trying to remove is the prejudice that fewer scalars was more natural. I think it's something which is, if you look at ultraviolet theories, they give you lots of scalars, and if you find one of those vacua which has a very small vacuum energy, then those scalars just tend to be light. So, but that was all within the context of derivative expansion. Now I want to convince you that you have no option about the derivative expansion. Essentially, everybody has to use it because that's the thing that justifies the semi-classical expansion, and which is what everybody's using when they analyze their theories. So here I've just written the Lagrangian again, but I've written now some of the terms involving curvature cubed. And so just so I can have an example of something which whose coefficient has inverse powers of mass as dimension. And I want to underline the fact that the scale that appears in front of the curvature cube term or any of the other terms is not the Planck scale. The way these extra terms are generated in a real theory would be we'd integrate out particles, and then a particle of mass m contributes to every interaction in the problem with m appearing on dimensional grounds. And if you add up all those particles, what happens if wherever m's in a numerator, it's the biggest mass that wins. If you're summing m squared over all m, then the biggest m wins. And that's kind of why we expect to see the Planck scale, say, in the Einstein-Hilbert term. But if it's in a denominator, it's the smallest mass that wins. And so the prejudice we should have is that the coefficient of something like a curvature cube term is the electron mass. It's the lightest thing we've integrated out before we write this effective theory down. And that's often people would say it's the Planck mass, and I'm just pointing out that that's actually a gross underestimated as the size of these effects. these higher curvature terms. Doesn't mean they're going to be big, but they're less suppressed than you might have thought. So now what we do is we calculate some process, a correlation function in cosmology or scattering, or you name it. You've got some Feynman graphs you calculate. This is the Lagrangian. All the terms that are in the Lagrangian, you can see how they appear in the observable just from the Feynman rules. They just appear as coefficients in the vertices. And then as long as there's only one scale at low energies, and so I'm going to assume that that's true, that all the momenta in the scattering are the same size as all the curvatures in the background. I'm going to call that H, that low energy scale, because I'm thinking of it as being the Hubble scale. So this would be something that the assumption I'm going to make would be appropriate for modes that are crossing the horizon during inflation, where the momenta are the same size as the Hubble scale. When there's only one scale at low energies, then you can just use dimensional analysis to see how it appears in the answer. And so then you can kind of identify how the low energy scales and high energy scales appear everywhere without actually having to do any real work. And I want to emphasize that it's just a dimensional argument. It's not relying on flat space Feynman graphs or anything special about a particular background. What you find is, if you're looking at a correlation function, is this expression here, which I'm going to interpret on the next page. So here's that formula again. And it's got the variables E counts the number of external lines in the correlation function you had. V sub n counts the number of times you used any particular interaction from the Lagrangian, and n just labels which interaction you're talking about. So V sub n equals 3 would be a graph which has 3 vertices from some specific interaction n. That interaction could have had d sub n derivatives, and that's what the product over d sub n is involved. So it's we're characterizing the interactions by the number of derivatives in them. So Einstein-Hilbert would be 2 derivatives, for example. And L is the number of loops in the graph. And so the important thing conceptually is that the thing that's circled here is that each loop factor costs you a factor of h over 4 pi m Planck, and that's kind of that's why the derivative expansion is the thing that controls the quantum corrections. Quantum corrections are more loops in this language. And if you're doing a classical approximation, you should always ask, why is it a good approximation? And the only known controlled answer to that question right now for gravity is the semi-classical expansion due to the derivative expansion. It doesn't mean you have to buy the derivative expansion, but if you have other ways of calculating, you have to justify why quantum corrections are controlled in order to convince people that you've controlled your theoretical error. But in the standard way people calculate, this is what's controlling it. And of course, this is a good approximation in things like inflation, where this particular ratio is not large because the Hubble scale is below the Planck scale. Now, the thing I've circled here now is this is all the contributions for the interactions with 4 or more derivatives. Those are the kind of the exotic ones that are more derivatives than the Einstein-Hilbert thing. And you can kind of see from this that H is always in the numerator. So the small scales in the numerator, you're always suppressed by at least 2 more powers of h over m Planck squared in addition to the loop ones. And then you have these factors of h over the little m, the scale that was controlling the higher derivative terms, which could have been the electron mass or whatever the last particle was you integrated out. The last term in this list are all the things that involve the zero derivative. So these are the interactions coming from the scalar potential. And these are dangerous because here's the only place where h is in the denominator. So if h is the small scale in your problem, then you can worry that if you're setting up a derivative expansion where it's powers of h over something, every time you use an interaction coming from the scalar potential, you're hurting that argument because you're introducing h's in the denominator. This is kind of the way you see that naturalness is classical inferences when you use the scalar potential are suspicious because using the scalar potential in a classical argument makes it compete with loop corrections with other interactions. And so that's special cases that are the naturalist problems, the dark energy problem and the scalar mass problems. But now we get away with it in cosmology normally because we've arranged V to be so small. And if H is the Hubble scale, then the Einstein equations say that H is of the order of V squared over M Planck. So that ratio of V to the 4th over H squared M Planck squared turns out to be order 1. And so in that regime where you're doing cosmology, those terms they're neutral. You can include them and they're not hurting you and they're not helping you. All right. Now, you should notice that there's no penalty in any of these expressions here for the fields being large, and that's kind of why transplanking issues are just a non-issue at low energies. If there's no energy cost for large fields, then there's no problem having them at low energies. There's also no penalty for 2 derivative terms, and that's kind of why the nonlinearities of general relativity are you can't neglect them just because you're at low energies. You're really forced to deal with them. But it also shows you why the 2 the sigma model interactions amongst the scalars are special because they're the ones that there's no penalty at low energies for using. If they were competing with general relativity, that would not make the derivative expansions suspicious because they have the same number of derivatives. Now, the problem is that when people look for scalar fields for the last 20 years, what they've done is on the grounds of simplicity, kind of very reasonably, they say, well, let's just add one scalar, see what it does, and trying to be systematic there. But the problem is that these derivative interactions involving scalars that want to compete with general relativity, field redefinitions can change them, and the coefficient, the coefficient curly g in this Lagrangian, the curly g acts like a metric in the target space, and field redefinitions are like coordinate transformations, and so the physical things only depend on geometrical things like curvatures. And so an example of that is scattering, this is something that's been known since the 80s, but particle physicists have been rediscovering it more recently. So whenever you have a flat target space, essentially, those derivative terms are not there. And if you have one scalar, every target space is flat because one-dimensional manifolds are all flat. So the one interesting interaction at low energies that competes with gravity is actually by accident not present if you have one scalar. And that's kind of why people spend so much time thinking about higher derivative interactions, is because they've specialized to one scalar field typically, and they normally get rid of the scalar potential by some shift symmetry because it's dangerous, then there's nothing left. And so the only thing you could look at are the higher derivative terms, and that's what leads you down the path of the Horndeski program, where people classify these higher derivative terms. And I would argue that that's actually probably not the right way to think about it. The right way to think about the things at low energies is the two derivatives, they want to compete with gravity. If you successfully make a four derivative term compete with gravity, then what you've really done is said that the derivative expansion is not very good, and so that your classical analysis that you use to infer its consequences are probably not reliable. But that's not a problem if the two derivative terms are competing. So we should be focusing on things with at least two scalars to explore those interactions, and that has not been done very much. And mostly I'd like to draw people's attention to that, because it's not very often there's virgin territory in an old field like cosmology or particle physics, but I think that is one. Systematically exploring multiple field models and how the two derivative interactions compete with gravity at low energies is a very underexplored area. And that's the direction I'd like to take you. So we have an opportunity here. I can kind of see that because I'm not showing you the slides as they would have been projected, you're seeing some slides that I had actually hidden. So that one doesn't matter. All right, so now I'd like to move on to, so if we're talking about multiple scalars, let's, what do they look like? And what are the simplest kinds of things we could think about, just as a benchmark to test how these two derivative interactions could be relevant at low energies? And I'm going to lead you towards a class that I think is fairly well motivated. So here we are, we have two scalars, then we're trying to understand what kind of choices we could have in the kinetic terms. We're really arguing about what kind of metrics could we have on the target space. And so a simplifying thing, since we're trying to get rid of the scalar potential as well, is to ask these scalars to be Goldstone bosons or pseudo Goldstone bosons. They might have a potential, but it'll be small because it's protected by a symmetry. And so that leads you to think about shift symmetries. And so I'm going to specialize for simplicity to the special case of two fields where one of the fields, I'm going to call it A for axion, has a shift symmetry like you would normally have thought about for an axion. The other field, tau, will also have a symmetry, but it's going to be a scale invariance, because I'm going to argue that scale invariances are very important symmetries. But because it's a scale invariance, the implications of that for the low energy theory are not quite the same. So in that framework, you have two Goldstone bosons. Only one of them really is required to have a shift symmetry. But that's actually nice because it means that the metric is characterized by one function. I'm calling it W squared here. And once you canonically normalize fields, then this W will appear in all the couplings of your problem. There's another function that it's not explicitly written here that is relevant, and that is when you couple to matter, the bottom line here, you have to say how the various scalars are going to couple. And when I get to if I get to the scale invariance part, the scale invariance says that the field tau, or chi, which is the canonical variable for tau, it couples as an exponential. So it couples as a Brans-Dicke field, in the sense that the matter couples to a metric, and that metric depends on the scalar field. That's going to be a consequence of scale invariance once I set up why scale invariance is important. So then the function that is in the metric is another thing you have to choose. All right. this is just emphasizing that the shift symmetries do not preclude there being interesting behavior in the metric. Sorry, I'll be thrown off a little bit by the slides I've hidden are here. So I'd like to zoom in now on a specific choice for these two scalars. And I'm going to use as my motivation that it's very often, part of what's going on in my motivation is that these shift symmetries for axions are generic in higher dimensional theories and in string theory in particular. But it's also true that scale invariance is generic in a specific sense coming from string vacuum. Every string vacuum you've ever heard about has at least one and usually more than one scale invariance. And the scale invariance Goldstone bosons tend to combine with the internal symmetry Goldstone bosons into supermultiplets in those kind of theories. And so I want to focus on an example where I have one of each, a scale invariance Goldstone boson and a shift symmetry Goldstone boson, and they're coming in a supersymmetric way. And as soon as I say supersymmetry, I can hear the eyes rolling around the room because you could say, well, why are we talking about supersymmetry given that we haven't seen supersymmetry? If it's not at the weak, if it's not at the LHC, why should we expect it to be at even lower energies at the small t? It turns out that's actually something that is also very generic, coming from string vacuum or from higher energy theories. What typically happens in a string vacuum, unless you engineer it not to happen, which sometimes people do, is when you break supersymmetry, the splitting of any particular multiplet depends on two things. It depends on the basic expectation value that breaks supersymmetry, which I'm calling F here. But it also depends on the coupling strength between the multiplet of interest to you and that field that acquired the expectation value F, which I'm calling G here. And so the splittings of a multiplet will be larger, the more strongly you couple to the field that is breaking supersymmetry. And in that picture, you can kind of see that gravity, which is typically interacting in the most weak way, will be split the least. And that's what you typically find when you start looking at vacua coming from the UV. Now, what can happen is, imagine that, so we got the gravity sector on the right here, which is split by less. The dotted lines are, the bosons, and the solid lines are the fermions, supermultiplet. And a matter sector could be a larger splitting, like on the left. Now, if your cutoff is here, that you can't actually measure anything above that scale, then what you should expect at low energies is that the gravity sector will be more supersymmetric than the particle physics sector and that's certainly a good summary of what we see. And so it turns out this is an observation that had been made in the 80s, I can remember. But what's different now is that people know how to couple supergravity to non-supersymmetric matter. So you can actually be very systematic about what this kind of framework would look like. And it's the kind of thing that is descends from low energies if, for example, supersymmetry is true in the bulk, but it's broken on a brane. Say, for example, if you have particles on a brane. And so it's the kind of thing that UV completions very easily give you, but which the low energy limit also accepts as being stable under radiative corrections once it's been given to you. So I'm thinking along those lines that the dark sector could very well be gravitationally coupled things. Those are like dirt in the UV completions of gravity. And supersymmetry could be playing a role there. And the scale invariances and the shift symmetries are also playing a role there. And I want to focus on the simplest example of that. So in that language, if it's a supersymmetric dark sector, then things are characterized by a superpotential and a Kähler function. And the shift symmetries are built in if the Kähler function is a function only of the real part of the supermultiplets. And there's expressions for those quantities, what I called Z of tau and A of tau in the previous slides, things you want to know. They're all derivable in terms of this Kähler function. And so here are expressions of what they would be. And when I show you the consequences of the models, what I will be doing is using this formalism, and I'll be taking the standard model and coupling it to a field like this. And although I won't show you the details, that's what's going on behind the board. And normally the details don't matter because the consequences that you derived in that way have very simple understanding in terms of symmetries. And I can kind of see that I've got 7 minutes left, so I might not have a lot of time for the symmetries. So let me what I'll do is I'll spend 4 minutes. I might cut to the chase here. I'll spend 4 minutes talking about the symmetries, and then I'll go right to what these models do when you look at their cosmology, because I'd like you to appreciate what the motivation of the models is. All right, so change of topic. What I want to do now is talk about supersymmetry and scale invariance and what that says about the corrections to the scalar potential and how it can help you with naturalness problems, which are the things that you worry about if you're trying to get low energy physics to emerge from a UV complete theory. All right. So I've told you some of the things that are common. You tend to find garden variety fields of low spin, and they're often coupled gravitationally. Supersymmetry is often present but broken. But what I want to focus on is a mechanism that's emerged that allows you to see why the scalar potential can be less corrected than you might have thought. So let me skip some of these things that are motivating it. This I've told you already. These would have been hidden. The most important thing is the scale invariances I'm talking about are these ones. So the metric scales by a constant factor. Other fields scale by different powers of that constant factor. And when that happens, the Lagrangian scales by another power of that factor. So it's not really a symmetry. The action is not invariant. But the classical equations of motion are. At least the leading ones are. Or if that's a symmetry, if that's a property that your Lagrangian has, the classical equations will be invariant under it. The reason that kind of symmetry is generic is easy to see in string theory. String theory has no small parameters, so all the expansions you do are expansions in powers of fields. And so you can imagine that schematically your Lagrangian comes to you as powers of the sums of monomials of these fields. And I'm running it schematically, there's derivatives of the fields. It's not just literally powers of the fields. But you can kind of see that if I scale the fields in some way, then any one term in that expansion scales in a specific way. And in particular, the leading term scales in that way. And so what happens in string theory is that the low energy limit implies this, the expansion in powers of alpha prime. The fact that you're at low energies, that's one of your expansion parameters. That's the field in string theory. That gives you a scale invariance right there. 11-dimensional supergravity has scale invariance because that's a low energy limit of string theory. But if you have also weak coupling, like 10-dimensional supersymmetry, supergravity, then you have another coupling. And so there's another scale, an independent scaling symmetry. So you have as many symmetries like this as you have expansion parameters in your problem, at least one, usually two or more. And that's the kind of symmetry I'm interested in for scale invariance. You can check that the various vacua have that symmetry. What's nice about those symmetries is they force the potential to be flat. If you have a minimum which breaks the symmetry, then it's connected by scale transformation to the scale invariant point, which had to have zero potential. So even though you've spontaneously broken the symmetry, it makes the bottom of potential zero, which is kind of unusual. It makes the cosmologic constant zero, even for a spontaneous breaking of the symmetry. But the problem with these symmetries is they're not quantum symmetries. They're not symmetry of the action. And so there was an industry in the 80s where people tried to exploit this and solve the cosmologic constant problem, which Weinberg shot down with his no-go theorem, essentially, in 1989. But what Weinberg doesn't show in his argument is how big the corrections are. And the question I'm heading towards is, can supersymmetry together with scale invariance suppress the size of the corrections? That's the thing for which there is now evidence coming from string vacua. And so let me cut to the chase here. The bottom line is that scale invariance and supersymmetry leads you to a class of theories that have flat potentials because scale invariance forces it on you. And those theories are called no-scale models. I apologize for these slides because I'm not showing you the non-hidden slides. You're seeing a bunch of slides that would not have been in the presentation. And I apologize for that. So let me cut to the slide that would have been seen. That is that basically the condition for a flat potential is something which was well understood in the 80s, and scale invariance is a sufficient condition for it. They're called no-scale models. But the observation is that there are no scale, although scale invariance is sufficient for a flat potential, it's not necessary. And so you can have a situation like this where you have a Kähler function, which is an expansion in powers of 1 over t, some large field. The first term in that expansion would be, say, linear in t. That has a flat potential because it's scale invariant. But the corrections to it, such as the second term here, which is independent of t, is still a no-scale model and has a flat potential. And it's only when you go to order 1 over t that you see that the scale invariance, the breaking of scale invariance has lifted the flatness of your potential. So there's a general class of theories for which scale invariance together with supersymmetry combine to make the corrections to your potential one order in perturbation theory smaller than you naively would have thought, even though scale invariance is being broken by quantum corrections. That's the class of theories that I'm heading you towards. And what I'm going to do now, because there's 2 minutes left, is to go to what those theories tell you. And so in the end of the day, I'm going to have an axiodilaton. The axion is an axion. It has a shift symmetry. The dilaton is enjoying one of these symmetries, which is scale invariant. And there's this mechanism that's making the corrections to its potential smaller than it would have otherwise have been. And I'm doing that in a way which makes the correction I'm going to choose this field to be so large that the corrections are as small as they possibly could be to see if that can help with the dark energy. And it turns out that it can. In ways that I won't have time to get to, but so let me skip now to the cosmology part of it. Oh, and these links that I built in that would take you through the theory aren't working anymore because I'm not. So I'll just have to scroll through these slides. I'm sorry. All right. So there's a class of theories that can make progress in the cosmological constant problem, but because they do, they're going to have light scalars in them. And so those light scalars, they want to be gravitationally coupled. They're dangerous. You should see them in the solar system. And so the problem with these theories is eventually it will be getting the vacuum energy to be the observed one, but it's already true that you can very easily understand why the potential could be smaller than it has to be to have the mass of these things be long enough that they could be appearing in experiments in the solar system. And so what I want to show you is some examples of, so I'm going to choose the coupling to be just big enough that it passes the solar system test and ask, can that kind of a particle have implications for cosmology? And you'll see that it will, because the scale invariant says that every mass in the standard model depends on this field. And so as the field rolls around, all your masses are changing in space and time. That sounds like it should be very dangerous, should be ruled out, but it turns out not to be. So I'm describing this. There's another way you can go where you try and screen things, which I will not talk about. So I want to show you these plots. So here's an example of a cosmology where this W function in the kinetic term has this exponential form. The scalar potential is, again, an exponential form or close to it because of the scale invariance. The U of X that's appearing there, I'll look at two cases where U is either a constant, so it really is a scaling form, or scale breaking can sometimes give you a shape to that potential U, and I'll assume it's a quadratic because that gives a small minimum. There's an exponential with a small divot in it, which gives you a minimum, because the cosmologies look a little bit different in those two cases, and I'll just explore that. So this is showing you the basic how the energy, the energy in all the various pieces of the fluid are behaving, and there will be also a potential for this axion field, but I'm going to treat it like an axion. And so the picture will be that the axion in this axio-dilaton combination is the dark matter, and the dilaton is the dark energy, but they talk to each other because of this W function couples them to each other, and so the mass of the axion and the mass of standard model particles care about where the dilaton is doing, and that gives you a lot of surprising consequences. But this slide just shows you that you can get the background that you're expanding around roughly looks right. This is what the fluctuations look like. This is the CMB prediction when you process this kind of a theory through class, which is the tools for doing this are the ones that are they're not very well developed, because there's a lot of, if you have a single field model, there's a lot of technology you can plug into directly to compare it to the CMB. And we had to do this by hand. Adam Smith mostly did this by hand, my collaborator, very good young student. But it's doable, and this is kind of what you get, and you see that and this is showing you as a function how things vary. The various curves have different values of this constant zeta, which is a parameter in the potential, and you see that sometimes you can see things, sometimes you can't. But if zeta is around 0.1, then basically that's not small enough that you hide things in the CMB. The basic effect that's going on for small multipoles it's the integrated Sachs-Wolf effect, is that now dark matter has more than one way to change. It doesn't just fall like 1/a cubed. It's got a mass dependence, which cares about what the dilaton is doing. And so that can be something which you see in it is changing the shape of the CMB. This is showing you how masses vary. In this case, the left is showing you what the dilaton does, and the right is showing you what the mass does of the various standard model particles. They all do the same thing. And so a lot of the tests of the equivalence principle don't care. But there's a phenomenon where you can't make the dilaton sit still. If you start it at rest at nucleosynthesis, because it's scale invariant, it goes into a tracker solution, and at radiation matter equality, that gets kicked into another tracker solution. There's a big transient that goes through, and that's still happening at recombination. So there's a generic prediction that masses are a little bit different at recombination, and this is kind of illustrating how big that is. It's the smaller you make the couplings, the smaller that effect is, and so this is not a large effect, because we chose the couplings to be small enough to escape solar system bounds. Same thing happens for dark matter, is what this thing says. The axion decay constant and the axion mass are both doing a similar thing because they know about the dilaton. And this is just showing you that there are effects for structure formation cares a little bit. And these two plots show you how that depends a little bit on whether or not the potential has a minimum or not. But it's something which is acceptable within what's been seen. But it's also shows you that there are potentially changes to be seen and to be sought by the observers. Probably what's the most interesting, given the recent DAISY.
Sorry, I got confused. Can I ask a question?
Well, it depends how much time we have. I know that I passed my thing has gone down, so the moderator should step in.
Sorry, 2-second question. In 2 slides ago, you said mass. It's mass of what particle?
This one was the axion, the dark matter, but the previous one was every standard model particle in the world has a field dependence to it.
Okay, thank you.
And so that there's a lot of things you have to worry about when you do that. So I can say more about that in the question period. All right. The last thing I wanted to say was, given the DAISY results, this paper came out actually 6 months ago, so it's not aimed at the DAISY results, but the DAISY results that are showing a hint for time dependence to the equation of state parameter. This is a theory which has got a positive energy. This is a plot of what the equation of state parameter is in that theory. It's always above -1 because it's just a scalar field. But if DAISY were to try to interpret its data for this theory using the way it does, what it assumes that there's dark matter which is falling like 1/a³, which doesn't care about the scalar field, and then the rest of it is the scalar field, which it thinks of as being a quintessence model, and it defines W for the rest of that it gets the equation of state parameter wrong because it's doing a bad job of the dark matter. The dark matter, because it depends on a scalar field which is rolling, is not evolving like 1/a³. And so because of that, DAISY gets what I'm going to call an effective equation of state parameter, which is not the real one, which is what I'm showing you here. It has this one. And you can see that it very easily can go into this phantom regime. And it's not because it's a phantom theory. It's just because the model that you're assuming you're comparing to is not the model that you actually are comparing to, because the dark matter and the dark energy are talking to each other. So unfortunately, the Z goes from left to right on one slide, and it goes right to left on the other slide. But you can kind of see that having a redshift of 3 pointing to you to a phantom regime is not crazy in this kind of a model. This isn't the fit I'm showing you. This is just showing you this is just what happens when you take it out of the box. And of course, one of the things we were trying to do now is to do fits to these data sets, because the models are very well motivated and they do very suggestive things precisely for the things that the data is pointing towards as being intention. This is a slide that I wasn't going to show you. So let me just conclude, because I know that I'm out of time, I think. So I have 3 conclusions. One of them is, I think it's really valuable to try and, there's many, many models you can make for dark matter and dark energy, and cosmology alone, the observation of cosmology alone will never tell you which one is right. There's just not enough information in the data. But the big clue is that what we're looking at is the low energy part of everything else we know about physics, and the things that cosmology likes are things that the low energy limit of higher energy physics hates. And that means that there's a very restrictive class of theories that we should be looking at. And then it might be true that the cosmology is enough to distinguish amongst those things. But there's an important clue that it's crazy to ignore, because it might be the most important clue in the problem. And of course, everybody has recognized that the cosmologic constant problem is a special case of that. If only there was a solution, then everyone would be happy to use it. And so I'm heading towards what I think will be a solution to that. But I think before you get there, you can already see that there are things, you don't have to use everything. You want to use the things that are generic at low energies as a clue in organizing your thinking about what you see in cosmology. And what you find can be very rich. Once you recognize that the small vacuum energy tends to come with light scalars, then the physics of light scalars is very rich. And in particular, the physics that wants to compete with gravity at low energies is the sigma model interactions, and that can be very rich, and it's very poorly explored right now. And so there could be many more things to be found there. Screening mechanisms, there could be interesting things in cosmology, tests of gravity, gravitational waves. It's really kind of a wide open area, and it's certainly well worth exploring. And we've focused on these axiodilaton models because I think they're very well motivated from the UV point of view. They satisfy this having minimal number of scalars to have these low energy interactions compete with gravity, but it's just a start, and there's probably much more to be found than what we found. But in that start, there's two things that we know GR gets wrong, and that's dark energy, dark matter. And there's two scalars you need to have things compete with gravity. Maybe we should take that as being telling us something. Maybe those two scalars are the two things that are the deviations from general relativity. Turns out that can work in this, at least in this axiodilaton context, and at least as far as we've pursued it so far. It may yet die on closer inspection, but surprisingly, it does things that are suggested in the data, but it wasn't designed to do them. It gives you changes to masses of particles dynamically at recombination, which is one of the leading proposals to solve the Hubble problem. I'm not saying these things do solve the Hubble problem, but one of the ingredients that we know should help is there. What's not normally tested in those models, those proposals, is they don't ask how the later time universe, when you do your fit, if you just change the mass by hand at recombination, you can't ask how does structure formation change down the road. But this is now I'm giving you a dynamical framework for that, where you can ask that. And that's what I'm hoping that our fits will tell us, whether or not that perhaps you lose the ability to help with the Hubble problem, but perhaps you don't, and we'll find out. Even more interesting, polarization is another thing that there's a hint for. This is an axion. It can have axion couplings to photons, and so all the stories that you hear about polarization could be there. They don't have to be there, but it's something which is suggestively there. And the evolution, of course, of the equation state parameter is very suggestive. So there's a variety of things that are already very attractive about these models. And so my main proposal is, or my main message is that it behooves thinking about this class of theories much more carefully. So thank you for your time. And I'm sorry for running over a little bit.
Anish writes me he got the freeze of his Zoom. So I think we have to self-organize.
Okay, I'm game. Whatever you want to do, I'm happy to do.
I have no idea. Maybe can I ask a question?
Please.
So sorry, two questions. So first, when previously you said that heavy particles can have a mass that change by 1%.
Yeah, that slide. I'll go back to that slide. Yeah.
Like maybe electron or proton or maybe the Z. So how is it possible that the potential of the light scalars remain small if they interact so much with heavy particles?
What's happening is that you've got a scale invariance, and so in the standard model, what happens is that the way that the dilaton appears is only through the metric, because it's like a Brans-Dicke coupling, and that makes a lot of the equivalence principle problems not a problem. For the same reasons for Brans-Dicke theories. But what happens is that anything in the Lagrangian which is not scale invariant, and so that's the mass terms, so the Higgs vev basically picks up a dependence on a non-derivative dependence on the scalar field once you canonically normalize everything. And so it's because of that every mass in the standard model gets the same dependence on this dilaton, except the neutrinos. And it's very suggestive. The neutrinos, if their mass comes from a dimension 5 term, they actually have a mass which is quadratic in the Higgs vev. So they get a dependence on the dilaton, which is the square of the generic standard model one. And that actually gives a numerology that actually makes sense. If there's a large field whose vev, this chi is the logarithm of field tau, and if tau has a large vev, it means that there should be a hierarchy between the neutrino masses and the standard model masses, which is set by the value of tau. And it turns out that there is a value of tau for which it all works. That when tau is 10 to the 28, depends how you normalize tau, but then the square root of tau is what controls the standard model mass. The basic scale in the problem is the Planck mass. The standard model masses all come in as the Planck mass divided by the square root of tau, which is the weak scale. And then the neutrinos come in as the Planck mass divided by tau, which is the electron volt scale. And it turns out that with this mechanism for suppressing the potential generically comes out to be the weak scale to the fourth, as it kind of has to be. But because of the supersymmetry in the problem, it comes to as a perfect square. So you can make a relaxation mechanism where where another field tries to minimize that. and it doesn't completely minimize it, and it reduces the answer from being the weak scale to, it turns out to be the Planck mass divided by tau is the scale of the vacuum energy, which is again the neutrino masses, which is the right order of magnitude. So it's one of those things where I wouldn't claim that there's a solution to the cosmological constant problem there yet, but it's a step in the right direction, because I can make things that are naturally very small. I can't give you 10 to the minus 120 in Planck units yet, but I can give you 10 to the minus 90. And that makes the real problem then in that language becomes the phenomenology of these scalars, which are coupling gravitationally in a potentially dangerous way. So the hope is that the cosmological constant problem can be rephrased as a model building issue for light scalars, for which there's much more hope for progress.
Okay. Maybe so. I can ask a second question if unless somebody. So the other question is, so I know there are other models now for the Desi anomaly where there is dark matter as maybe a heavy fermion, and its mass depends on the vacuum expectation value of a scalar. And in these models, fitting the Desi anomaly needs that the mass of dark matter increases with time. So I was wondering, if the same happens in these other models where dark matter is an oscillating action.
So that I think is a more model dependent conclusion in the model I'm talking about. If I'm looking at the right slide here, yeah, this is the right hand panel here is the axion mass, and so you can kind of see that and then the top two graphs are the ones where the potential is a pure exponential, and so then it turns out the mass is actually a decreasing function in this case. But in the case where there's a minimum, what happens is that you get oscillations, and so it's one of those things where that. Okay. The growth is a model dependent thing. It's not generic.
Okay, so it's different. Okay, thank you.
Thank you.
And if somebody has other questions, we need to self-organize.
Well, there's another talk, I think, very soon, right? So it's the schedule I was sent, it had a talk after mine. I was I think it was. It was
well, okay, I hope Anish will recover his crashed computer.
What I'll do is I'll stop sharing it, and that way if there's a
Okay.
I don't see our next speaker here either, so
okay, I have no idea. Okay. So I suppose now I should say thank you.
Good to see you. Anyway, thank you for the invitation.
Okay, not for okay. Thank you.
All right. So take care.
Okay, I don't know if I should close the. Sorry, Shuntaro has a question.
Yes, good. All right.
No, just I'm saying thank you.
He's just.
Thank
All right.
you for a nice talk. Yeah.
Okay.
Thank you. Bye-bye.